Hey guys, so this is the first video that deals with our new topic in part 4, special relativity. And I just want to show you on our course page, if you scroll down here, this is where I'm going to park all the videos that I do on the PowerPoint presentations. Okay, so far I have 4 videos produced, short videos that go through the PowerPoints of these 4 topics. So my recommendation is grab these PowerPoints and you can read them before you look at the videos. That would probably be the best thing. But then the idea is you can run the videos. You'll see me going through these with some audio commentary. Okay, but it's not, the videos are not the same as you guys reading these PowerPoints. Okay, all right. So let's do the first topic, which is an introduction to what a relativity theory is. It's called Newtonian Relativity. So I'm going to go to the PowerPoint. Here it is right here. So the first question is, what is a theory of relativity? And really what we're going to do in a theory of relativity is we want to relate the physics of one observer to the physics of another observer. And if the two observers are at rest with respect to each other, then that's a pretty trivial case. Everything looks the same. But when one observer is moving relative to another observer, that's when you're going to need a relativity theory to relate the physics of both observers. So more formally, and in a picture that we're going to use and use and use and use in this topic, I want you guys to imagine a set of XYZ axes like you see right here. And then also the person in this spatial coordinate system, they need a timepiece because time is an integral part, right, of physical processes. So those 4 variables, position, x, y, z coordinates, and time t, that forms what we would call a frame of reference. Okay, so you'll hear that terminology a lot too. And traditionally, we call the frames S and S prime, as you'll see. So imagine that there's an observer in frame S, which is a set of XYZ perpendicular axes, and then some sort of clock to keep track of time. And you can even think of the observer as at the origin of the frame if you want, which I'll sometimes mention that. Okay? Now, an event is something that is measured at a position and a time. It can be an actual process, such as a light going on or a light going off, or it could just be an object occupies a point XYZ at some time t. But in any case, a measurement of position and time is a measurement of an event, okay, as you can see indicated there in that figure. All right, so now what I want you to imagine is that there's another observer moving relative to the first observer. That observer that's moving relative to the first has his or her own frame of reference. And you can see that right down here as we've indicated. We're going to call that frame that's moving relative to the first frame, frame S prime. So there's going to be a set of X prime, Y prime, Z prime axes, and then a clock measuring time T prime. Now what we're going to do is whatever the direction of the relative motion is, we're always going to say that's the common XX prime direction. So the XX prime axes will always be collinear. And then the speed of the observer, the velocity of the observer, relative to the first observer, we're going to call V. So we would say that the whole frame S prime in this picture, 1.2, is moving to the right at velocity v. Okay? Okay. When we do these diagrams, these SS prime diagrams, it's conventional to have S prime going to the right at some speed v. Okay? But you could draw it the other way. It's just that the equations that we're going to develop are going to assume that v is to the right. Okay. So what we're going to do first is we're going to form what's called Newtonian relativity, which is the relativity that we're used to when we use regular old so-called classical physics. So I want you guys to imagine down here that there is going to be an event, okay? But to make our equations a little bit simpler, here's what we're going to assume. As you can see in figure 1.3a, frame S prime is moving to the right. And as a practical way to think about this, you could think of somebody in frame S standing on the sidewalk. A car would be frame S prime. Somebody driving down Central Avenue, okay, at a constant speed. To make the equation simpler, let's assume that the two origins coincide at both t and t prime equals 0. So we're going to agree to that. So again, that makes the equations easier. All right, so let's suppose that happens, and a little bit later at time t, an event occurs. You can see that over here in figure 1.3. So maybe if we go back to Central Avenue, maybe there is a bird lands on a tree. Okay, so you standing on the sidewalk, you're going to measure the position of the bird at that time, and then your friend driving in the car in frame S prime, they're going to measure the position of the bird at that time. Now, as you can see right here, during that time, frame S prime has moved a distance of v times t in frame S. Okay, so that's going to be critical, because if we go to compare the measured positions and times in the two frames, I think you can see in this picture that the y values are going to be the same, as are the z values. There is going to be disagreement on the x values. For the person in frame S, they're going to measure this long distance x right here. For the person in frame S prime, who you can think of at the origin O prime, they're going to measure this shorter distance x prime. Well, how much shorter is it than the longer x? This distance right here, this distance of travel, vt. So we can write down almost immediately that x prime is going to be x minus vt, y prime is y, z prime is z, and as far as we know, right, everybody measures the same time, whether you're moving relative to somebody or not. We'll see that that's not the case in general, but in our everyday life, that's what it looks like. Okay, so these equations, 1.1, this is a statement of a relativity theory. We call these equations the Galilean transformation equations, and these form the basis of what we call Newtonian relativity, which is the relativity that we're used to in our everyday lives. Okay, now once we have these, we can get a lot more physics, because what we can do is we can differentiate these with respect to time, and we can get velocity transforms. We can then, right, we can compare velocities of objects moving in frame S and S prime. We can differentiate the velocities and get accelerations. We can find momentum transformation equations, energy transformation equations, all starting with these Galilean transformation equations. In fact, if we do the velocity transformations, we're going to get these right here in 1.2. So ux prime would be the x component of the velocity of the object moving in S prime. U sub x would be the velocity x component of the object measured in frame S. V we're going to keep for the velocities between the two frames of reference, the two observers. So any object that's moving, we'll say, has velocity u with x, y, z components. You can then differentiate these velocity components and find out that the acceleration components of an object moving in both frames will be the same. Okay, as you can see right here. Now, if you actually want to see the derivation of these velocity and acceleration transformation equations, that's done on the next slide. Okay, and what you end, it's some nice calculus. What you do is, let's just take a quick look at the first one. I don't want to bore you with the details, but you would start out and you would say, okay, the x component of velocity u prime by definition is dx prime dt prime. But then you use the chain rule and you write that, you write that as dx prime dt times dt dt prime. Then you substitute in the transformation equation for x prime, which is x minus vt. And since t prime equals t, that dt dt prime derivative is 1. So then you end up just differentiating x minus vt. You get dx dt minus dv dt over dt. Dx dt we recognize is the definition of the velocity x component measured in frame s, and then dvt dt is just v. I should mention that we are assuming that the velocity between the observers is a constant. All right, so that's what, in fact, makes this topic special relativity. We're assuming that the velocity is a constant. Okay, you can do a similar thing for the yz components, and you can do a similar thing for the acceleration components if you want, okay, to go through the details. Okay, so that's it for the transformation equations for Newtonian relativity. Here's an example of how this formally would look. Suppose that Jack is standing on the sidewalk and Jill is driving down the road at 35 miles per hour relative to Jack. So here's a picture right here. Here's Jack stationary here. Here's Jill right here. And suppose there's a bird flying between them, flying towards Jill, and Jack measures it to be flying at 5 miles per hour. Okay? So if I ask you, how fast does Jill see the bird flying, you might think about it in your head and say, okay, look, she's going 35 miles per hour to the right relative to Jack. The bird's going 5 miles per hour relative to the right. So it looks like Jill would see the bird traveling at 30 miles per hour. But if you think about it, right, she's pulling ahead of the bird. So if you ask Jill, she would say, well, I see the bird going this way to the left at 30 miles per hour. And in fact, that's what the transformation equation will give you. Right? In this picture, we can call Jack unprime, put him in frame S, Jill's prime in frame S prime, right? The relative speed between these two, v, is 35 miles per hour. The bird's velocity measured by Jack would be u sub x. We'll assume it's just x motion. That would be plus 5 miles per hour. Therefore, the velocity measured by Jill would be u prime sub x. And using the transformation equation right here, u prime sub x equals u sub x minus v, you get 5 minus 35, or negative 30 miles per hour. What's the negative sign tell you? That for Jill, the bird's moving to the left, right? Because again, she's pulling ahead of the bird, okay? What if the velocity of the bird, right, is the other way? So in other words, the bird is flying towards Jack relative to Jack at 5 miles per hour. Well, then it would see, right, Jill would see the bird moving to the left even faster. And in fact, if you do it, you'll get negative 40 miles per hour. Okay? All right. So in Newtonian relativity, observers in relative motion can measure different velocities for the same object, but they will measure the same accelerations, changes in velocities. So there's a little introduction to what we mean by relativity theory. I'm going to end right now.